A uniform horizontal 300 Newton beam, 5 meters long, is suspended vertically from its two ends by a rope. If a 600 Newton person stands 1.5 Newton from its left end, find the tension in each of the ropes. Okay, so this is a static equilibrium problem, and our first step will be to represent the problem diagrammatically to understand it. So, a uniform horizontal 300 Newton beam, we can represent the beam like this: uniform and horizontal, 5 meters long. So this is 5 meters long. Is suspended vertically from its two ends by ropes, or by a rope. So from that end, a rope is suspended on a rope. So let's call this end point A, and let's call this end, the right end, point B. So these two ropes is holding this beam vertically at two ends. And now, uniform horizontal 300 newtons. What it means is that we can assume that the weight of this beam will be concentrated at the center. That is 2.5 meters from either end. So 300 Newton is acting at the center. Uniform horizontal 300 Newton beam, 5 meter long, is suspended vertically from its two ends by a rope. If a 600 Newton person stands 1.5 meters from its left end, so this is the left end, this is 2.5, so if 1.5 should be somewhere here, so we have a 600 Newton person standing here, so his force will act downwards his weight will act downwards with a force of 600 newtons from 1.5 meters from this end. 1.5 meters. Then we're now asked, find the tension in each of the ropes. So we can assume this free body diagram is in equilibrium. And so what in equilibrium means that it's balanced, and then let's take the tension on this rope to be TA and the tension on this rope to be TB. So if it's in equilibrium, then upward forces will be equal to downward forces. So we can say TA plus TB, upward forces and downward forces is equal to 600 plus 300, which is 900 newtons. Let's call this equation 1. So TA plus TB is 900 newtons. Now we're asked, find the tension in each of the ropes. How will we find the tension in each of the ropes? Okay, we've gotten one equation, free body diagram, in equilibrium, upward forces equal to downward forces. Now we have two unknowns in this equation. We can use moments to resolve the forces, and if we take moments about this point A, that way it's a technique to cancel out this this TA. So if you have one unknown, we can easily find out the unknown. Let me explain. Moment is force times distance about a point. So if we take moments about this point A, TA is 0 meters from that point, and whatever the force is times that 0 will be equal to 0, right? So if we take moments about point A, one thing about moments for a body in equilibrium is clockwise moments is equal to anti-clockwise moments. So if we take moments about point A, we can say TA will cancel out. So TA times 0 plus clockwise moment. TB is going to give us an anti-clockwise moment. So anti-clockwise moment will be equal to clockwise moments, and the TB will be TB times 5. TB times 5. Moments, force times distance, right? About a point. So these are the anti-clockwise forces. Then the clockwise forces are going to be this 600 newtons and this 300 newtons. So this person standing here, his own moment will be 600 times 1.5. And the moment about at the result of the weight of the beam with 300 times 2.5 plus 300 2.5. So basically this equation says anti-clockwise moments is equal to clockwise moments. That's for a body in equilibrium. So of course we say that TA will go to 0, TA times 0 is 0. So 5 TB is equal to 900 plus 750 is equal to 1650 newtons. And so TB is 1650 all over 5, which is equal to 330 newtons. So if TB is 330 newtons, we can come to equation A to find that TA will be equal to 900 minus TB is equal to 900 minus 330. So TA will be 570 newtons. So TA is 570 newtons, TB is 330 newtons. And so those are the tensions at each end of the rope. If you want to check it, you can also check. Another way is to take moments about B. If you do that, you're going to, it's another way to help us. TB will cancel out, and A, we can find TA. But this way is simple enough. And with this solution, we can see that our answer is A. That's the tension in the ropes.